morning. Our first speaker this morning is Hiroaki Terao, who will be speaking on ideal subarrangements of Weyl arrangements.
Okay, thank you very much for giving me a chance to give a talk here. So I will talk about some new class of free arrangements, and that is this story is related to yesterday's talk by Dr. Slofstra. I don't know if my pronunciation is correct. But okay, so anyway, I will give you some new class of subarrangements of Weyl arrangements which are free and also with interesting properties. So let me begin. So this is actually a paper. This is a report of a paper authored by 5 people. So 5 is a big number. Actually, this is the most number, the biggest number I had as number of authors. So 4 co-authors together. And actually, what happened to create this paper is about a year ago, I made a trip to Germany to collaborate with these 3 people. But they are very, very good at finding, checking arrangement is free or not by using a lot of computer time. But they are very innovative about developing a new program. And I went to Germany to sell this program about the ideal subarrangement together with Takuro Abe. So this paper, and that my sales trip was successful, and they bought this project, and they checked. They almost immediately, maybe 2 weeks, it took almost 2 weeks to check that this conjecture is true. Okay, I will tell you about the conjecture. But after that, we tried to prove without using any computer and purely theoretical proof again. So we gave. So I'd like to talk about this. Okay. So and this paper is on here, and this will appear in the Journal of European Society probably this year, I hope. Okay, so let me begin. Okay, the first, okay, probably no need to remind you that we consider Weyl arrangement, which is simply a reflection arrangement which comes from a root system. So you have a root system over Z, then you have a reflection hyperplane, because that group. That if you have a root system, of course you have a Weyl group, and Weyl group contains many reflections, and you consider all the reflecting hyperplane. And that is called Weyl arrangement of hyperplane. And so this lattice, and of course this lattice, so phi is a root system, so if you consider this lattice, of course this is stable under the Weyl group. Weyl group is denoted by this one. Okay. And this is the set of positive roots. This appeared already yesterday's talk. And also this we consider simple system. Simple system, existence of simple system is of course very, very important. Okay, so we use this notation like this root system phi and the positive roots and the simple. Okay, so first I will define this so-called root poset. Okay, this is also kind of standard, I guess. So you consider the set of positive roots, and you you introduce this partial order, which is beta 1 is greater than beta 2 or equal, that is beta 1 minus beta 2, can be of course written as a linear combination of simples, but all the quotients should be non-negative. Okay? And this makes this set, and the set of positive roots makes this set as a poset. So we call this positive root poset or simply root poset. And the ideal is simply this is if you consider this as a poset, this is a lower closed system. Okay, so if you have a beta 1 is in I, beta 2 is lower than beta 2 in this sense, then beta 2 should be I. Okay, so this is kind of also rather standard, I guess. Okay, and now when you have this I ideal, then of course this I gives you a subset of a Weyl arrangement, which is simply you consider every element of I, and you consider the kind of perpendicular hyperplane, which is denoted as the kernel alpha, and this is the arrangement, of course. This is a subarrangement of Weyl arrangement. So this arrangement is naturally called ideal subarrangement. Okay, so this is a subarrangement of Weyl arrangement, but a special kind of subarrangement. And of course, you probably I will give at least one example, which is this type A3 case. This is very well known that this is positives. They are simples. And of course, the order is like this. For example, these orders is this. So for example, if you take this one, this is an ideal because this is the lower closed under the operation taking the lower element. But this is not an ideal because alpha 1 plus alpha 2, 3 is there. But for example, alpha 1, alpha 2 is not there. So this is not ideal, this is an ideal. Okay? So there are, of course, any subset can be ideal or non-ideal. Okay? And I'd like to note that this entire set, entire positives, of course, is an ideal. Okay? This is just like the whole ring is an ideal, whole quantitative ring is an ideal. Okay, so I will kind of quickly review the concept of free arrangements. Okay, so you can forget Weyl arrangement for a moment, and we just consider the general arrangement of hyperplanes in LD-dimensional vector space. Okay, so we assume that all hyperplanes are going to the origin of this V. Okay? So sometimes it's called the central arrangement. Okay, so we use this notation. So alpha H is in V star. This is vector space, and this is dual space, and this is in H. Okay? So we take, for every H, you can pick alpha H. Alpha sub H is determined up to constant multiple, non-zero constant multiple. And S is a symmetric algebra of the dual space V star. So this actually can be regarded as an algebra of all polynomial functions on V. Okay? So yes, this is also standard. And this is maybe not yet as standard as these, which is but rather a good history, which is called sometimes it's called a derivation module or logarithmic derivation module, which is defined this way. Okay? So we consider all the derivations from S to S, from S to S itself, and that should be R-linear, but also they should satisfy derivation conditions, which is sometimes called the Leibniz rule. So for example, F times G operates is sent to F times theta G plus G times theta F, and so on. You know very well. Okay? And this condition is the most important condition here, which is that if you operate this theta derivation to this alpha sub H, which is a defining equation, in a sense, defining equation of this hyperplane H, then this result is again polynomial, again inside of S, should be divisible by alpha H. Okay? So this should belong to the ideal, principal ideal generated by alpha H. Okay? So this is the function. Okay, so this is the graded module, easily, and this is submodule of all derivations. Okay. And but this derivation module is not necessarily a free module, but sometimes it's free module and sometimes it's not free. So if it's free module, we call this A is free arrangement. So this is the definition of free arrangement. And for free arrangement, you can find homogeneous basis. This is graded S module, so always you can find homogeneous basis, and the rank of this module is equal to L. L is the dimension of the total space here. Okay? And you can consider degrees of these derivations. This degree is simply the derivations of the quotient of those derivations. Okay? So these non-negative integers d1 to dl, they are non-negative integers. This can be 0, but that cannot be negative. They are called the exponents. Of course, the exponents do not depend upon the choice of a basis. Of course, there are infinitely many choices of homogeneous basis, but these exponents is well defined. Okay, and this is a kind of classical theorem. This is at least latest at 1976, Kyoji Saito knew this theorem already, and this is a total Weyl arrangement. Okay, so not the ideal subarrangement, the total Weyl arrangement is a free arrangement, and the exponent of a Weyl arrangement coincides with the exponent of the corresponding rule system. So this exponent of corresponding rule system is very, very, very known, and this theorem says that new exponents defined using the concept of free arrangement coincide with the old exponents, traditional exponents of the system. And maybe this is just simply one example. So this is a type of B2. So this is very simple arrangement. This contains 4 lines. And this is one operator. This is sometimes called the Weyl derivation. This satisfies the condition to be in there. And also the theta 2, this one, also in there. And it's not difficult to check that these two form a basis, homogeneous basis for this module. So this is free arrangement, and the exponent is 1 and 3. 1 is because this degree is 1, x1, x2, they are degree 1, x1 cube, x2 cube, they are degree 3. So 1 and 3 are exponents. Okay, so, and there is this is also very old theorem, okay, more than 30 years ago. And this is a free arrangement. For any free arrangement, you can have a DL. Then this has some topological meaning. Of course, this has a combinatorial meaning also. But here, I would like to emphasize the topological meaning. So this is that we consider inside of complex space. This is a complement. So this is a Stein manifold, non-compact, and this M of A. This is of course a manifold, and you can define that Poincare polynomial. You can define Betti numbers Poincare polynomial. Then this Poincare polynomial has a factor like this, 1 plus DIT. Here DIs are 6 points. Okay, so these are kind of a review of, and these are, of course, you know, so probably we skip these, but I just want to remind you that we have a classification of Weyl group or the root system. So, and these are kind of interesting numbers, they are exponents. And there's 4, 1, 5, 7, 11, and this is 1, 5. Okay. This is the end of the list. Okay, so now I'm ready to state the main theorem here, the only one main theorem, which is if you consider the irreducible system of rank L. Okay, so you can just classify this. So this is somewhere between A and G. Okay? And I is an ideal. I just define ideal. Okay? And then ideal, every ideal defines so-called ideal subarrangement. This is the ideal, this I contains these positive roots, and for each positive root you have a hyperplane, and you just collect all the hyperplanes, then that is the so-called ideal subarrangement. So now we started from the ideal, and we have some arrangement, which is ideal subarrangement. And then the two results, one is a B free arrangement, in the sense I just mentioned. And the second, the exponents. If you have a free arrangement, you have exponents, and the exponents and so-called height distribution of the positive root in I satisfy the dual partition formula. So dual partition formula is the same thing as yesterday's talk. It was called constant McDonald, Steinberg, Shapiro. I don't know which order, but this is the same thing if B is A itself. If B is the entire case, this formula is a similar formula, not similar, same formula as the theorem which was mentioned yesterday. Okay, so, and actually this result, yeah, also yesterday this was mentioned, I believe. Somers, Kimosto, these two people made some conjecture about the ideal subarrangement. And this settles their conjecture. Actually, I did not know, we did not know such a conjecture existed, and we just uploaded this result to the archive. Then I received an email from Somers 2 days later, and this was a conjecture we posed. And actually, they checked for at least type A, B, C, probably D, but with using classification. And our proof does not use the classification, okay? And also covers the exceptional cases. Okay, so in particular, this is already something I already mentioned, okay, which is that this part I already mentioned, which is if ideal itself is equal to the entire positive root. In that case, our main theorem, of course, our main theorem can be applied because this entire set is an ideal. So in that case, we have the dual partition formula by Shapiro, Steinberg, Constant, McDonald. Okay? And this is this. Okay? It's the same state. Okay, so let me, I believe probably this part you don't need that, but just on the safe side, I'd like to review this height here. So height is simply just for any positive root can be written this way, and the Ci are non-negative integers, so we just simply add all these coefficients. Then of course this is positive integer, and this is called height. So that, for example, simple roots have height 1, right? And the height distribution is simply the numbers of heights of, and the number of positive roots of a given height. For example, I1 is equal to the number of positive roots of height 1, so which is equal to actually the number of roots of height 1 is equal to the number of simple roots. Right? So this is equal to L actually, total dimension. In this case. I2 is a height 2, corresponding to height 2, and up to IM. This is M is a maximum height inside of this. So I will give you a very simple example here. So probably this is enough. Okay, so type E6 case, this is height 1, this is height 2. Height 2 is of course the sum of two roots. So these are of course corresponding to each edge here. So there are 5 edges, so there are 5 roots of height 2. And height 3 is corresponding to like alpha 1 plus alpha 3 plus alpha 4, or like alpha 2 plus alpha 3 plus alpha 4, and so on. Okay? So there are now, this number is now this not number, this expression of roots becomes longer and longer, of course, because height is higher. So I skip this part. But this is height 11 is the highest root, which has these quotients. Okay? So if you add 1 plus 2 plus 2 plus 3 plus 3 plus 1, which is 11, so height 11. Okay? So what is so this is height, future height. So these are height 1, height 2, height 3, these are too long. So I just simply put dots here. Okay? And this is the highest root. So alpha tilde is equal to this. Okay? And then this is height distribution, because these are the height using height. So height distribution is starting from 6, 6, 5, 5, 5, 4, 3, 3, 3, 3, 3 to 1, 1, 1. And of course, if you add them up, of course, this is equal to the number of positive roots, which is the number of hyperplanes inside of Weyl arrangement of type E6. And also, I'd like to talk about exponents. Exponents can be written this way, okay? If 1, 4, 5, 7, 8, 11, so this is an 11, 8, 7, 5, 4, 1. And if you compose two pictures, the picture is like this, okay? So these are height distribution, these are exponents, okay? So this picture just simply says that the dual partition theorem. So if you count horizontally, you have height distribution. If you count vertically, you give an exponent. This is our famous theorem, celebrated theorem by Constant and other people. Okay, so let me very briefly review the history of this dual partition formula. Okay, first Arnold Shapiro using a classification, and he was the first one who noticed there is such a beautiful relationship. And 59, but he did not publish any paper. And actually, Robert Steinberg, in his paper in 1959, at the end, he mentioned that Shapiro already has this observation. Okay? So by using that classification, and Steinberg wrote briefly about this result, but also he used the classification. And the first proof without using classification is by Constant, and this is the first part of this Constant paper, and he mentioned that the very important question is that this agreement is more than just a coincidence, remained open, but he gave a proof. And also later, I.G. McDonald gave a proof, another proof using generating functions. It's a completely different proof. And here, this ABCHT is our paper, we proved that this is a partition formula for any ideal subarrangement. So of course this is the generalization of these results. And here also we used a completely different method by compared to these two earlier proofs. And we using a free arrangement theory. So this is totally different. So in a sense, this is a new proof of this theorem itself. Okay, so, and this is actually the key theorem. This is the total theorem which lies in totally inside of arrangement theory, free arrangement theory. But this is a really key. And if you find this one, then it's not so difficult to check that their partition formula for any ideal subarrangement. So I'd like to use a little time to explain this. Okay, so the theorem tells something like this. If you have a free arrangement, then the question is this: how can we add new hyperplane without destroying a freeness? Okay? So A prime is free, and for example, if you want to add one hyperplane, in that case, this criterion is completely known, which is called addition theorem, which was a long time ago, maybe 1981 or something like that. So, but this is different from that addition theorem. This is multiple addition theorem. The multiple because we want to add new hyperplanes at once, several hyperplanes at once. Okay, so the statement is this: if A prime is a free arrangement with exponents and exponents are this increasing order, and we assume that the highest exponent appears p times. Okay, so dl is the highest exponent because this. But it's possible that there are many highest exponents. So P is the number of exponents. Then I'd like to add new hyperplanes. These are new hyperplanes. And so new hyperplanes, of course, these do not belong to this A prime because A prime is the original one. And define this one. Okay, this is a little bit hard to read, but this is simply restriction of this arrangement onto this Hj. For each j. Okay, j is fixed here. J is between 1 and q, and then you fix hj, and you consider all the intersection of this hj and h. H is moving and a prime. Okay, so just imagine that you have a new hyperplane hj, and you have other hyperplane like h, and you consider this codimension 2. Each codimension 2 space. Okay? So this codimension 2 space can be considered as a hyperplane inside of Hj, right? Because Hj is codimension 1. So this is a new arrangement here. Okay? So arrangement theory can be used to here. Okay? And assume that these three conditions are satisfied. Okay, one condition is this: H1 intersected with HQ, Q codimension. So in a sense, this is the fault that those hyperplanes are linearly independent. And the second condition is this X. This is the codimension Q subspace should not be inside of all hyperplanes. This is second condition. And the third condition is you consider the difference between the number of hyperplane here and the number of hyperplane in this restriction. This number is by definition of restriction. This is more than 0. This is positive integer. But this should be equal to this D. D is the highest exponent. Okay, so this is actually a very strong condition. This kind of thing seldom occurs, but if this occurs for any j, then you can add these hyperplanes without destroying the freeness. And also the exponents perform this way. Exponent is I said that we have a p highest exponent and p q exponent. Out of those p exponents should go up by 1. So this is d plus 1 appears q times. So this also shows that if such a thing exists, then q should not exceed p. So p is the number of highest exponents, and q, if such a q exists, then q should satisfy this number. Okay.
So does this include the addition theorem that you mentioned earlier?
Yeah, actually this does not contain addition theorem, because this is a very good question. Thank you. Okay, the point that such a theorem is possible because we are only considering the highest exponents. But addition theorem also you consider not highest exponent. Other exponents can go up. But in this case, only highest exponent one. Highest exponent is very special. We are using the speciality of this highest exponent to prove this theorem. Okay. So I will not go into the theorem of the proof. Okay, so main theorem is like this. I just already mentioned. Okay. So I have not so much time, so I will go slowly, not slowly. So E is an idea about it. Okay, A is a resistance. But this is just outline. Okay. So if K, then we consider such a thing. Okay, this is subarrangement of this ideal subarrangement. We want to prove that this B is free and with a good exponent. And this BK is simply just this is filtered in a sense by K. We only consider up to some height. Okay. Then B1 is just a part of simple roots. Right? So this is a free arrangement, and the exponent is like. So this is starting point. And we use this MAT multiple addition theorem, which I just mentioned, to this BK to BK plus 1. This is A prime and this is A. So the difference is, of course, the number of, positive roots of height K plus 1, exactly K plus 1, which is inside of this B. Okay, this is a difference. Okay, and to verify two assumptions, we verify some corresponding combinatorial geometric properties. And I will just tell you one result, which we used as a lemma. Okay. So probably it's not so difficult to check, but actually this was the last piece we found to prove this theorem, which is this. Okay. So if you have a height alpha, if you have a height over alpha, okay, we consider this such a thing. X is in L of A. You can consider such a thing. X. This is just a perpendicular thing to X, orthogonal hyperplane, or not orthogonal space to X. Okay, and we consider this subset of phi. Okay, then this is the root system again, and we have this alpha, and this is of course height minus 1, but this is kind of local height. Alpha inside of this phi x denoted by this way, and this minus 1, and you just add all the hyperplane, all the hyperplane in A upper alpha. A upper alpha is the restriction. Okay, so in a sense, we say that this controls this global height and local height can be connected this way. This fact is used here. Okay, and the proof goes this way. So starting from scratch, this is height 1, height 2, height 3, and please note that at this moment, these are exponents, 1, 2, 3, 3, 3, 3. So we have a many highest exponents. And next we pick, so only highest exponents goes up. This is only highest exponents goes up. Highest exponent, highest exponent, highest, 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 highest. Now that this is the story. Okay? So this just tells you how to prove this. Okay, so this is a summary. Okay, this dual partition formula by Shapiro, Steinberg, Constant, MacDonald can be generalized to a class of ideals, and the theory of free arrangement, especially the multiple addition theorem, provides the base of our proof, and our proof uses some combinatorial geometric properties concerning the hyperpositive. And let me conclude my talk with this natural question. So we know that this is if this F is subset, and F then but question is this. Okay, is there any nice characterization of this set? This is same thing as saying that which subarrangement of Weyl arrangement is free or not. Okay, so this is not so easy question probably, but at least we know that if you have an ideal, and if you send this ideal by this element of a Weyl group, of course this corresponding to a free arrangement. So at least this contains this. And also yesterday's talk by Dr. Slofstra, and he mentioned about that X sub W, and for each Weyl arrangement you have some free arrangement, I think. So obviously that there is some gap, and I'd like to know how big is this gap, and if there are also any good class between them, and which can be proved to be free without using classification. So I stop here.